this last topic in chapter 1, which is we have here the power losses, and then we will discuss about the snubber circuit, and lastly the last subtopic, which is the cooling and heating dissipation method, okay, for power electronic circuit. So power losses, okay, it can be we can divide it in general due to the parasitic losses, okay. So actually the parasitic losses is actually that we cannot avoid. Okay, we cannot avoid these losses. This is due to the internal winding of the cable itself. Okay, because we use a cable. Okay, so inside that cable we have core, and each material have their own internal resistance. Okay, so we cannot avoid that. Okay, and then we have also dielectric losses inside the capacitors. And also the losses, the parasitic losses that due to the eddy and hysteresis losses. This is where you have, is actually inside the transformer. Okay, inside the transformer, because in the power electronic circuit, we still use transformer to either to step up or step down. This is usually when we apply it in the grid connection. Okay, because to have to connect the grid, so we need some isolation between the power electronic circuit and the grid. Okay, so this is maybe due to the transformer and so on. Okay, this one is actually we cannot avoid. Okay, the second general losses that associate with the power electronic is actually from the power switches itself. Okay, where this one is actually very significant. Okay, the losses is very significant, but however we can manage it. Okay, we can manage it, or we can actually try to reduce the loss. So inside these power switches losses, we can divide it into 3 losses, which is the conduction losses. Okay, this is actually we can say that on state losses during on. So what is the losses? Okay, and then we have blocking losses. This is during off state. And the other one is the switching. These losses, the switching losses, is when it's actually in the transition between on and off, okay, and off to on. So between the switching, there is also losses. So we will actually go more on these 3 losses, okay. So forward conduction losses, or is actually losses that associate when the switch is turned on, okay. And these losses is measured at lower frequency operation, which is maybe switching is 50 hertz, 100 hertz, and so on. So these losses is more towards when you are operated at a very slow frequency switching. Okay, so what is the switching? What is the forward conduction losses? Is actually we can calculate by using this one. So P on, we stated that this is a definition for the, this is the symbol for the forward conduction losses. P on is equal to the voltage across the switch multiplied with the IF. So meaning that when it is in on state, okay, so you have switch right now is open, but right now the switch is closed. Okay, the switch is closed. So the voltage across here, it maybe have some V drop. Okay, that's why V drop or Vs on. Okay, so very minimum here. This is actually equals also to V forward. Okay, V forward. And since this is turned on, so meaning that the current is flowing inside this switch. So the voltage drop multiplied with the current flowing, I have current forward. So there will be some power absorbed, okay, power losses inside this switch. Okay, that is what we call the forward conduction losses. Okay. So this is example of an on state voltage is, for example, we have the V forward, voltage forward during the power, when the diode is in forward bias. Okay, and then the current flow inside that diode. So the voltage drop multiplied with the current, so it will be have a power losses. Okay, for example, you have, for example, the diode, the voltage drop is very, very small. I think maybe for example, 0.5, for example, we take, okay, so V forward. So when it is turned on, so we have V forward is equal to 0.5. Okay, 0.5. So it's very small. Okay, but you need to take note that when the diode is forward biased, the current that flow inside this diode, which is IF, is maybe from 100 to 1000 amperes flow. So maybe for example, 1000 amperes. So the power on losses is actually 0.5 multiplied with 1000. So you have 500 watt losses there. So very significant. So actually, the conduction losses is very significant in the power electronics. Okay, so that is the first losses. The second losses is actually associated with when the switch is turned off, is at off condition. Okay, at off condition. So when power is switched at off state, it will withstand high voltage. This is a voltage blocking. Okay, and this can up to 100 to 1000 volt depending on your circuit. Okay, and for example, like this, you have switch, and this switch is actually turned off. Okay, but there will be a voltage blocking here, and depends on the circuit. Okay, but since we know that for the practical switch, even though it is open, but there will be some leakage current will flow inside this, but this leakage current is not very, very, very high. So it's actually up to micro to milliamperes. So so as you can see here, P off or P blocking is equals to V blocking multiplied with the current, leakage current. Since the current leakage current is very, very small, microampere, so usually you have the power losses, but it's not very significant compared to the on-state losses. Okay, so if compared to the forward losses or on-state losses, so blocking state can be considered is very, very minimum losses. And the last one is the switching losses. Okay, so due to the current and voltage changing simultaneously during the switching period, and this switching losses is very significant. Okay, the losses is very significant when your switch is switching at very high frequency. Okay, so where is actually this switching occurs is actually like this. Okay, for example, this is V off, so this is current. Which one is the current? Okay, this is current. So meaning that this is actually off state. Okay, off state, and this is on state. And then this is off state. So as you can see, this is the, between this off and on, there is a transition from off to on. And as you can see, there is some delay here. The voltage is actually slowly going to zero. And at the same time, the current is rising. Okay, the current is rising. So as you can see here, there is an overlap between the voltage and the current. Okay, and also here, there is an overlap between the voltage and the current. So the overlapping will introduce the P switching losses. Okay, here. So this is where the switching losses occurs. Okay, so meaning that if you are switched at very high switching frequency, so there are more switching losses. Okay, so for the on-state losses, it is measured when you are actually at lower frequency operation. While for the switching losses, it is very significant when you switch at very high switching frequency. Okay, so this is actually the pictures that shows about the switching losses. Okay, so this is actually the pictures, the previous pictures, and this is actually, as you can see, this is the power waveform. Okay, power waveform, which is this is the switching losses here. Okay, so this one you can ignore. Okay, this one you can ignore. I may accidentally put it here, but this one is not covered. Should be, you can ignore, but this one maybe is good for your information. Okay, but it is not covered actually inside your syllabus. Okay, we have already completed the 3 losses. Okay, so very important to know. So we have conduction losses. Okay, and then second one is the blocking losses, and the last one is the switching losses. So how to minimize the power switches losses? So there are 2 methods that you can use. The first method is what we call the snubbering, where actually this snubbering is actually you need to install, or you need to design another circuit, and then this circuit will be connected parallel with the switches. Okay, so there are extra circuit. The second one is by programming. You need to program the switching time, okay, of the power switch, so that the switching occurs at 0 voltage and 0 current, meaning that the transition, meaning that it is actually avoid the overlapping between the voltage and current. Okay, so you can program it. You need to use some programming, okay, so that you can minimize the switching losses. Okay, so sometimes this one you can, if you are actually go for the final year project under power electronics, so if your lecturers ask you to design a switching technique, okay, to minimize the power losses, so this one, the method is actually popularly known as a ZVS and also ZCS. Okay, so 0 voltage switching and 0 current switching. So this technique is also actually, in general, it is called a soft switching technique. Okay. Okay, so the second subtopic inside this chapter, the last section here, is the snubbers. So these snubbers is actually an extra circuit. Okay, you need to design. So you need to design that circuit, but it's actually not very. It depends on the application. So it is not compulsory to be there. Okay. So the first one, this is the function, is actually to protect the power switches, meaning that it limits the stress on switch to save values, and at the same time also it will divert the energy during the switching transition from switch to another circuit, where it can actually reduce the power losses. Okay. So this is the function of the snubber circuit. Okay. So this is actually the snubber circuit. Okay. So as you can see, we have a transistor here, and to avoid or to make this transistor to be operating at a very safe condition, so we need to put an extra circuit, okay, in parallel each switch. Okay, so this circuit is actually connected parallel for each switch. So this one we call the RCD type. So what is RCD? Why it is RCD? Because we have a resistor, we have capacitor, and we have diode. So that's why we have RCD. Okay. So actually, what this RCD do is this RCD number circuit do is actually, as you can see from the previous from this figure here. Okay, for example, you have these transistors and connected with a volt VDC, and this actually switch on and off. Okay, you have these signals, and then this signal is actually give signals on and off. Okay, so meaning that you will obtain your VCE here, the voltage. If you put your oscilloscope here, so you will see that this one is 0, maybe this one 5 volt. Okay, this one from electronics, from your microprocessor, and let's say that your V in is actually 100 volts. Okay, so this signal is come from your microprocessor and then go to the gate driver, and then it will turn on these transistors, for example here. So if you put your oscilloscope, okay, you will see that there's a waveform that follow the signals. Okay, because the signal is on, off, so it will follow the same signal, but the voltage here is 100 volt because it is connected to the DC source. Okay. Okay, but as you can see here, we have LS, or we sometimes this one is actually stray inductance. This stray inductance is actually not purposely there. Okay, this stray inductance is actually what we call a parasitic element. We cannot avoid that. Okay, this stray inductance usually it can be easily created due to your improper wiring. Okay, for example, if you have a lot of cables, okay, jumper wire here and there, so which is orang kata apa, berserabut kan. Okay, you have a lot of cables jumping here and there. Okay, so it will accidentally create this inductance. This is what we call stray inductance. And this stray inductance will affect in the operation of the whole circuit, especially for the transistors. Okay, what happened here is actually this, you know that inductance is energy storage element. Okay, so when this transistor is turned on, a current will flow here and this inductor will store some energy. Okay, and when this transistor is turned off, so this energy inside the inductor will release that energy. So that's why, as you can see here, we have some overshoot spike, because this is actually where the energy from the inductor is discharged. Okay, so this is very dangerous, okay, to the transistor. It will actually destroy this transistor at very long time period of time. So it will shorten the life of the transistor, because usually this overshoot strike, okay, so meaning that every time a switch, it will create some spike. Okay, this spike may be 5 times from 100 volt, maybe 500 volt. It can be up to 500 volts. So every time it switch on and off, so spike 500, 500. So it will actually destroy these transistors. Okay, so how to avoid or how to actually reduce this effect, okay, is actually to make sure that where this one, as you can see, the function of the stubber is to limit the stress on the switch to safe values. Okay, So here we have the snubber here, RCD, where it's actually create an alternative way for this energy from the inductor to be divert into another circuit. Instead of releasing the energy and then go straight to the transistor, so this circuit will actually will divert the energy from the inductor into this circuit so that the voltage across the transistor will be a very smooth transition. Okay, no overshoot. Okay, because we know that we have inductor here and we have the capacitor here. So the energy inside this inductor will be absorbed by this capacitor. Okay, because we know capacitor is also the energy storage. So the energy come from the inductor. You need some energy storage also to actually absorb the energy. Okay, so that is how this snubber circuit operate. But this snubber circuit usually they have already integrated inside the transistors. Okay, some of the transistor, for example, IGBT or MOSFET, depending on the manufacturer, they have already installed or they have already integrated this snubber circuit inside their transistors. Okay, so this one I think we can skip. Okay, so this is the power switches cooling, which is I have already, I think, show you in the previous class. So it is very important to make sure that the temperature at the switch is maintained at its optimum temperature. For example, maybe 65 degrees, okay, maintains. Okay, so you need to maintain that temperature. So to maintain that temperature, so we need to have some cooling method, okay, so that the heat can be transferred to the environment. Okay, because if the temperature is very, very hot, so it will damage the operation of the circuit and so on. Okay, so the heat transfer can be accomplished by either conduction, convection, or radiation. So, for example, we can use what we call the heat sink. Okay, this heat sink, which is I think the most cheapest solution to for this power switches cooling. And then we also can use water cooling effect. Okay, so meaning that we have a water flow so that the water can absorb the energy. It's like macam car radiator lah. So it will absorb all the energy and so on. Okay, I think that's all from me. Oh, cepat ni. Setengah jam je. Okay, so this one is actually this is RCD numbers. Okay, so this one, if as you can see, this one is actually the waveform that shows if you have different C actually, different capacitor installed. Okay, so you need to make sure that the capacitor that you install is appropriately, because if you the capacitor, this one is a this one is C1, for example, this one is C2, and this one is C3. So C3 is bigger than C2, and C2 is bigger than C1. So if your capacitor is very, very big, you will see that the transition between this one is on and this one is off. Okay, because the on here, because the current is flowing, so that's why I say that is on state. So the transition between on and off will become longer, okay, which is not good. Okay, so we want to avoid this delay here. Okay, so it is important to calculate the correct capacitor so that it will be not affect the transition between on and off. Okay.
tahu which capacitor is appropriate for this circuit.
Sorry? Oh, which capacitor? Actually, this one is a qualitative analysis. We don't have any analysis here. Okay, so just to show you that you need to properly select a proper capacitor. Just this one is just to show to show you the effect of the capacitor itself. So meaning that you need to properly select capacitor. But inside the syllabus, we don't cover the analysis of what is the suitable capacitor value. Okay, this is just to show you the effect of if you choose wrongly the capacitor. But right now, a modern IGBT MOSFET, they have integrated the number circuit inside their transistors. I don't have with me right now. We have actually a module. Okay, so like this one is a single transistor, and since this one, it will not have a snubber circuit because this one is a single transistor here. We have a transistor that integrated a snubber circuit, but that one, the shape is quite different from this. It looks like a block, okay? Because inside that, they integrated the circuit already inside that transistors. Okay, so this one is actually an example on actually why this inductor will give the output of the transistor VCE like this. Okay, because as you can see here, this is the voltage across the inductor. Okay, the voltage across the inductor. And as you can see, this is the voltage of the transistor. So the voltage input plus the voltage across due to the inductor. Okay, and this stray inductance is due to the improper PCB layout or improper wire loops. Okay, for example, wire loops is like this. If you have wire here, okay, jumping from this terminal to this terminal, it actually creates, because each wire will actually have a current flow. So if there is a current flow inside this wire and then there is a current flow inside this wire, it will have some mutual inductance created between these cables. Okay, so it will create a snubber, we create what we call the stray inductance. So in electronic circuit or power electronic circuit, we avoid to use jumper wire. Okay, and the PCB layout also will produce some stray inductance if not properly designed. For example, that's why some of the circuit, they properly place the transistors, all the components very near to each other, because they want to avoid they want to avoid this part, okay, because they want to avoid dia punya laluan current tu kalau boleh orang kata apa, the current punya part tu, the current part as small as possible. Okay, like this. Itulah. That's why sometimes as you can see, this is a very compact. This is an industrial standard. So it's actually a very compact circuit. As you can see, all are very near to each other because we want to avoid the current part. Okay, kalau boleh nak very short. Okay. And then what else? This one's numbering lah. Tak ada apa. And then I think that's all from me for this class today. So yesterday, viral professors punya videos. One professor from UITM.
Viral doktor.
Viral